get the cool. All right, we are thrilled to have today Damian. Alex did a PhD at Princeton, and he recently graduated, and now he's a postdoc at Kemper Institute here at Harvard. And he's going to soon join MIT EECS in math. He's done a lot of super interesting work in deep learning theory and optimization, and today he's going to talk about why gradient flow is broken and how to fix it. So thanks, Alex, for the talk.
Thanks, Blake, for the introduction. So yeah, I'm going to be talking today about a recent paper on understanding optimization in deep learning using a new theoretical tool that we developed called central flows. So this is with my amazing collaborator, Jeremy Cohen, with whom I work very closely on this project, and additionally Zipra Coulter, Amit Tolkar, and Jason Lee was my advisor. So I want to start by just giving a brief outline of this talk. So I'm going to start by talking about the simplest possible optimizer that we use to train neural networks, which is just gradient descent, specifically full batch gradient descent. And I'm going to show how these dynamics for gradient descent are going to be governed by this new phenomenon called the edge of stability. So I'll talk about what exactly that means. I'm then going to describe how this raises a lot of challenges for classical optimization theory and why it invalidates most classical optimization theory. And in the second part, I'm going to talk about what we can do to actually fix it. So how can we develop a theory of optimization and deep learning that actually does apply to the way that we train neural networks? And at the end, I'm going to show how we can generalize this technique to understand adaptive optimizers like ADA, which are actually state-of-the-art for training large models. So before I get further into this talk, I want to add a huge disclaimer, which is that nothing in this talk is rigorous. So I had some previous papers where I tried to actually analyze optimization rigorously. There are a lot of technical challenges that come up, and if I have time, I'll describe at the end what I believe is the path forward to making this type of theory rigorous. But this talk is not a rigorous talk, but it's incredibly predictive. So kind of the burden, the way we measure success for this type of theory is whether or not we're able to predict concrete things about optimization on real neural networks. And hopefully there will be some actual rigorous theory that follows. So I want to start just by talking about gradient descent. So by gradient descent, I mean that you're just going to compute full batch gradients over all of your data points, and then take a step with learning rate eta in the negative gradient direction. So this is definitely the simplest possible optimizer. And a lot of the intuition for gradient descent, and at least the way people analyze gradient descent, you can already see in one dimension on a quadratic. So if your quadratic here is just 1/2 SW squared, so this is a one-dimensional quadratic, then you can just write out the gradient descent update, and you'll get the W gets multiplied by the scalar 1 minus eta s at every step. So this immediately gives you two regimes. If this scalar is less than 1, then the dynamics are stable, and you'll converge exponentially fast towards 0. So this is good. On the other hand, if this value has absolute value greater than 1, then you'll begin to diverge exponentially, bouncing from side to side at every step. And we're going to call this unstable. And so if you want to just optimize a quadratic, in this case, this 1D quadratic, you definitely want to make sure you're in this regime. And in particular, you should set your step size small enough so that this constant 1 minus eta s is less than 1. That way you'll actually converge. So this is clearly necessary for quadratics, and one of the amazing results in classical optimization theory is that this is sufficient with a lot of generality. So in particular, the classical theory says that gradient descent will converge as long as you promise me that the operator norm of the Hessian, which is going to take the place of this S, is bounded by 2 over my current learning rate. So as long as my learning rate is sufficiently small, I'll make this value sufficiently large, and it'll dominate the Hessian of a loss, and then I'll get good convergence. So as I'm aware, almost every theorem in classical optimization theory is going to rely on some assumption that looks like this. And you'll justify it by saying this is clearly necessary for quadratics. So this seems like a nice story, but where does it actually break down? So to show how this breaks down in deep learning, I want to give you an animation of a real neural network and what happens when you train it with gradient descent. So here I'm plotting the dynamics of a vision transformer, so this is not a toy model, on CIFAR10, an image classification data set. And what I'm plotting here in the x direction is the sharpest direction of the loss landscape. So this is the top eigenvector of the Hessian. In the direction that it moves to and from the camera, I'm plotting the progress direction. So this is the direction in which the loss will actually go down. And in an xy point in space, the z direction is just going to represent the loss at that point in space. So I'm going to zoom in and just start running gradient descent. So at the beginning, this is kind of exactly the picture of gradient descent that people expect. The loss is going down, you're moving down this valley. This seems nice. So now in the background, I've colored in red this scary region in which the Hessian is going to be too large for gradient descent. In particular, it's the points W, which the operator norm of the Hessian at those weights W is going to be larger than 2 over eta, meaning that if I drop gradient descent in one of these red points, gradient descent will blow up exponentially fast. And this is because, unlike quadratics, neural network loss landscapes are not just quadratic, meaning that the Hessian can change from point to point. So there are going to be points like this blue region where the Hessian is going to be relatively small, and points like the red region where the Hessian is going to be relatively large. And you can actually see that we seem to be approaching this red region. And in fact, if you just continue training, you'll always end up in this red region. So this is not just some artifact of a vision transformer or some artifact of CFAR10 or some artifact of the learning rate that I've picked. It turns out that for any model, for almost any reasonable learning rate and any data set, you'll always end up in this red region. You'll always end up in a region where gradient descent is unstable. So what happens next? Again, if this were just a quadratic, you would expect a picture like this. You'd expect it to begin to blow up exponentially fast. So for people who haven't seen this before, does anyone have a guess for what's about to happen? Try to visualize what's going to happen. To me, it was very counterintuitive. It looks like this. So you do enter this red region a little bit, and then after you enter the red region, you do blow up, which is what you would expect from a quadratic Taylor extension. But then afterwards, you get catapulted back into this blue region. And so now you're kind of bouncing between these blue and red regions, essentially for the rest of training. And you can actually show that for the rest of training, in any reasonable empirical setup, any transformer, any model, any data set, any learning rate, almost all of training will occur in a regime that looks like this. So this was given the very catchy name, the edge of stability, from this paper from my collaborator, Deriving in 2021. And he actually demonstrated by just doing an insane sweep over so many different settings that this is the typical regime for gradient descent in deep learning. So he also pointed out in this paper that the edge of stability is inconsistent with existing optimization theory. So specifically, if your optimization theory depends on any sort of smoothness assumptions, these are invalid. If you rely on monotone descent, meaning that the loss has to decrease monotonically for gradient descent, this is not going to be true. Because you can even see in this animation that the loss goes up and down as you're oscillating in this valley. It invalidates any optimization theory that's based on a quadratic Taylor expansion of the loss, because as I mentioned, for quadratics, this can't happen. And it also invalidates any heuristics for step size selection in terms of the Hessian. So if you open an optimization book, one of the first things it'll tell you is that you should set your learning rate to something like 1 over the top eigenvalue of the Hessian. This is a reasonable learning rate to use. But the Hessian's changing. So 1 over the top eigenvalue where?
Can we ask questions?
Of course.
So in practice, we use much smaller learning. Atom will converge to 10 to the minus 6 or 10 to the minus 7, which is nothing like 2 over the biggest thing. Can you comment on that?
So we'll come back to Atom. The learning rate for Atom is a bit misleading because the preconditioner, like the denominator, will give you a different effective learning rate.
No, it's not just 30%. But it's preconditioned with momentum.
I agree. So I'm actually going to talk about Atom at the end. Atom is in exactly the same regime. The Atom picture looks exactly like this.
Okay.
For Atom, it's not 2 over Hessian, it's a different condition that's more subtle that involves a preconditioner, but Atom does not escape this. Yeah. So the last thing is, like, you could imagine, like you were mentioning, okay, what if I just shrink the learning rate? Maybe this learning rate's just too big. So it turns out that if you want to escape this, I can imagine here, okay, I shrink the learning rate and this will push back the red region a little bit. But then once I hit the red region again, I'm going to have to shrink it again and again and again. And you can actually show that if you try and play this game where you're constantly trying to shrink your learning rate with the Hessian, you will never converge on any reasonable model. It'll take you an order of magnitude more steps, possibly multiple orders of magnitude more steps, if you try and play this game where you avoid the edge of stability. And kind of the weird thing is that the edge of stability is not bad for optimization. I'll show you later some plots, but in other directions, the loss is still going down. So this turns out not to be a bad thing. It's actually a feature, not a bug. So I want to describe how you can actually understand these dynamics. So a full optimization trajectory will look like this. On the left, I'm plotting the loss, and on the right, I'm plotting the top eigenvalue of the Hessian. And at the beginning of training, the top eigenvalue of the Hessian just goes up really fast until you've hit this red region above 2 over eta, where it's expected to be unstable. And then it's just bouncing in and out of this red region for the rest of training. So this is exactly what this picture I showed you in the last slide was. It's that this top eigenvalue of the Hessian, which I'm defining to be the sharpness, is just bouncing up and down. But despite that, the loss still goes down. And it's not monotonic, but it goes down pretty fast. So if you try to use a smaller learning rate, you get a picture like this. It's slower at the beginning, but then eventually even the smaller learning rate will have edge of stability at a different threshold, and it'll still make the loss go down, but it's actually slower. So the fact that you spend more time not in the edge stability is not a good thing. You're just going to converge slower and you gain nothing. So you really should just embrace the fact that larger learning rates are better and that this edge stability phenomenon is not actually so bad for convergence. So then the question is just like, what is happening in this crazy regime where the sharpness seems to be stabilizing around 2/eta, and then the losses continue to go down? So this is essentially the main point of the talk. I'm going to start by analyzing this for gradient descent, and then I'm going to describe how this extends to adaptive optimizers like Adam. So the goal of this talk is to characterize the trajectory taken by an oscillatory optimizer. And this is an optimizer that over short timescales is going through crazy oscillations in weight space, but over the long term, hopefully will follow some predictable trajectory. So the way we actually analyze an optimizer is the optimizer itself is this blue trajectory, it's oscillatory, but we're going to derive what we call a central flow. So a central flow is a differential equation that is attempting to model this time average of this oscillatory process. It's the central flow. And this is in contrast to something like the gradient flow, which is just what happens if you take your step size to be sufficiently small. And we show that the gradient flow is actually a terrible approximation to gradient descent at the edge stability, but our central flow is a very good approximation because it actually takes into account the effects of the oscillations. And then empirically, once we get the formulas for these central flows, we test them. So we go back to these neural network settings that I described earlier, and we just compute this central flow. We discretize this flow, we solve the ODE, and then we show that it's actually matching the trajectory of gradient descent in weight space and in all derived metrics. And finally, once we have these nice formulas for the central flows, we can interpret these flows to actually better understand and gain some intuition for optimizers like gradient descent and Adam. So this is the game plan. And I want to start by just deriving our first central flow for gradient descent. This is
a quick question. I mean, what you said all makes sense. Do you have any a priori reason to think that the central flow is better in terms of performance and so forth than the gradient flow if you could compute the gradient flow?
So there are two things. The first is that, yes, we have reasons to believe that in the sense that you'll get better generalization and there's all sorts of other downstream properties. We can't prove these, but empirically they're true. But the other thing that I think is more interesting is that the gradient flow is inherently undiscretizable. And what I mean by this is that
Yeah, I know, it's a very hard thing to get. Okay.
Whereas like it's actually very easy to discretize the central flow. And this is because the central flow is going to have bounded curvature, and things with bounded curvature are easy to discretize. But actually, I think the main point is not that it's a good optimizer, but it's just that it's what gradient descent does. So if you want to understand gradient descent, you should think of it as the central flow. And I'm going to justify this later on.
The 3D graphic that you had, could you like the gradient flow would be just the direction of the progress?
Correct.
And where would in that animation, where would the central flow be? Like
The central flow would just stay put. I'll describe this in a second, but it would just stay put without oscillating. Because here I only plotted two directions of the lost landscape. The lost landscape has billions of directions. In these two directions, it's going to be stagnant. In other directions, it'll continue to make progress. But I'll have some more animations for this later on. Yeah. So how do we derive the central flow? So we're given some oscillatory optimizer. This is WT. This is going to be our gradient descent. And pictorially, what we want is some W bar T, which is going to be our central flow, which is going to pass through the midpoints of this process. In general, the oscillation can look much more complex and chaotic than this, but this is just a nice cartoon. So we're going to pretend mathematically that gradient descent does oscillate around a central flow. I've not defined anything yet. This is purely a pretend. I'm just going to posit the existence of such a central flow W bar, and I'm going to try and derive some conditions that it must satisfy. So the first thing that we can notice is that we can actually put an additional constraint, which is that you oscillate along the top Hessian eigenvector. So in the quadratic case, you begin to blow up only in the directions where the corresponding eigenvalue is above 2/eta. So if only one eigenvalue is above this critical threshold, you're going to oscillate along the corresponding eigenvector. So we're going to assume that WT oscillates around W bar in the U direction, where U is the top Hessian eigenvector. This is just a modeling assumption. So mathematically, we're going to just write this formula, that W can be decomposed into this central flow W bar plus an oscillation in the U direction with magnitude X. And now the question is, how do we actually compute W bar? So there are two steps. The first is we're going to treat this oscillation as a random variable. It's not random, it's chaotic, but we can close our eyes and pretend it's a random variable for now, because it's just an oscillatory object. So we're going to compute how the oscillation variance, sigma squared, which is going to be the variance of these oscillations, will affect the average gradient, i.e. how it affects the overall trajectory taken by W bar. The idea here is that the gradient here and the gradient here are different from the gradient at W bar, and W bar will move in accordance with the average gradient of all these oscillations. So we have to compute this. Yeah.
Why is the top eigenvector fixed?
It's not. Locally,
So
it's
U is a, so it's not.
It should also be U sub T.
U's of t. Okay.
Yeah.
All right.
But over short periods of time, we're going to treat U as fixed.
Good.
Yeah.
Okay.
So yeah, given a sigma squared, we're going to assume we know sigma squared first. I can then compute which direction W bar will move. And then the next thing is we saw empirically that gradient descent equilibrated its top eigenvalue at 2 over eta. So we're just going to force this as a hard constraint on our central flow. The central flow is not allowed to have any Hessian eigenvalues above 2 over eta. And it turns out that these two constraints are going to be enough to analytically solve for the trajectory of W bar. And I want to just describe this calculation because it's very short. So the first is, how does the oscillation variance affect the average gradient? And this is just a Taylor expansion. So if I start by Taylor expanding the loss, I'm looking at the gradient at W bar plus x to u, so the gradient at Wt. And I can just Taylor expand this in x, and I'm going to get this power series, where the first term is going to be the gradient at W bar. The second term is going to be an oscillation term, which is essentially just going to tell me I'm oscillating up and down. And then the third term is going to be something different. So this is a single gradient, and I want to compute the average gradient. So I'm just going to take an expectation at both sides. And here the only thing that I'm assuming is changing is x. Over short timescales, I'm going to assume that u is the same, W bar is the same, and I'm just going to assume that x is changing. And now we have some simplifications. So the first is that I'm assuming that this is a random variable where W bar is the mean. If W bar is the mean, then x has to have mean 0. So this whole term will disappear from the average gradient. And essentially, this is just because if I look at gradients of successive steps, they'll cancel each other out. This term will be pointing up on this iterate, pointing down on this iterate, so over time, the average is to 0. And this one, we've already assumed that the expectation of x squared is sigma squared. So we have a formula for this one as well. And putting everything together, you get this formula for the average gradient. And now this looks a little scary. It's like a third derivative of a boss, so this is a 3 tensor, and I'm applying it to the top eigenvector of the Hessian. But if you're familiar with this formula, this is just the formula for the derivative of an eigenvalue. So as long as the eigenvalue has multiplicity 1, it's differentiable. And this is exactly the formula for its derivative. So I can simplify this further. And the key lemma is that the average gradient is just going to be the overall gradient plus a curvature penalty, which penalizes the gradient of the top eigenvalue of the Hessian. So now at least I can describe the dynamics in this 3D animation. What happens is first, the average gradient has sigma squared very small. So you just converge into this valley and you enter the red region. Once you've entered the red region, you begin to blow up exponentially. So sigma squared starts to increase. Once sigma squared starts to increase, this curvature penalty kicks in, which points you back towards the blue region. It's the gradient of the sharpness. So you're effectively doing gradient descent on the top eigenvalue, and pulls you back towards the blue region. Afterwards, you're back in the blue region, you're stable again. So gradient descent will again force the oscillations down to 0. Sigma squared goes back to 0, and you again just follow the gradient at the bottom, which will again force you back into the red region. And you get this loop. So this is a negative feedback loop that tries to maintain stability of the algorithm. So the important point here is just that the oscillations induce a curvature penalty, that's the goal, and the curvature penalty is proportional to the variance of the oscillations. So now we're just going to assume that W bar follows this average gradient. We don't know sigma squared, we don't know the variance with which we oscillate, but if we did, then W bar would have to follow this differential equation, where you just follow negative eta times the average gradient. And now our goal is to solve for sigma squared. Is everyone following the calculation so far? Great. So step 2 is, what is sigma squared? And this is now an easy calculation because we have this extra condition that we need the sharpness to be less than 2 over eta. And in fact, when we hit edge of stability, the sharpness is exactly 2 over eta. So we can start using the chain rule. We're now in continuous time, not in discrete time, and continuous time gives us a lot of tools. So first, if the sharpness is exactly 2 over eta, then the derivative of the sharpness with respect to time has to be 0. But we can expand this using the chain rule. So using the chain rule, the derivative of the sharpness with respect to time is the gradient of the sharpness times dw dt. And we have a formula for dwt that we've posited at the top in terms of our unknown sigma squared. So we can plug it in. Now, if this quantity is 0, this is just a linear equation for sigma squared, and we can solve for it. So these two terms actually have some simple interpretations. This first term is if sigma squared was 0, and this tells us how fast is the top eigenvalue increasing if we weren't oscillating. So how fast are we entering this red region in the 3D animation? The second term is telling us if we oscillate with variance sigma squared, how fast is the sharpness going down? How aggressively is it pushing us back? And it's just saying that the oscillations are going to stabilize at some value where these two terms balance. And you can just solve for it and you get some value for sigma squared. And then you plug it back into our ansatz for W bar, And this gives you the gradient descent central flow. This is just a differential equation that you can now simulate. Any questions about the derivation? Great. So you can also extend this to multiple oscillating directions. I'm not going to spend too much time on this, but the math here is actually significantly prettier than the math for one unstable direction. So you essentially do the same thing. You assume that you oscillate around some central flow W bar with some variance sigma that's unknown. And the average gradient you can now compute, and it's very similar, where you get the gradient at the valley floor plus some curvature penalty. And you now have to solve for sigma. And we essentially show that there's only one choice of sigma that satisfies three very benign conditions. So the first is sigma is an oscillation matrix. It's a covariance matrix. So it should be PSD. This is a fairly reasonable assumption. The second is stability, as before. So the top eigenvalue of the Hessian has to be bounded by 2 over eta. And the third is complementarity. So before we said that you only oscillate along the top eigenvector of the Hessian. Now you oscillate in the span of all unstable eigenvectors, but there can be multiple. And we show that these three conditions turn out to be enough to uniquely determine sigma. And the type of object that you get at the end is what's called a differential complementarity problem. So this is related to the theory of complementarity, specifically semi-definite complementarity problems. But these can be efficiently simulated. There are numerical solvers for them, and we essentially use one of these numerical solvers to simulate our central flows. So what is the picture? What are we really saying here? So the classical picture of gradient descent is that there's some stable region in which the Hessian is small. This is the region in which you expect gradient descent to work. And inside of this region, you just hope that you stay inside this region so that you can get convergence. But the real picture of gradient descent in deep learning is very different. It all operates at the boundary. So early on in training, you're pulled towards the boundary of this set, and then the rest of training happens along the boundary of this set. And what's happening in each of these is exactly this picture, where you enter the red region and then bounce out. And in this picture, the central flow is just going to follow gradient descent for the beginning, and then it's just going to traverse the boundary exactly, rather than oscillating inside and outside of the boundary. So mathematically, we can also reinterpret the formula for gradient descent in terms of projected gradient flow. So I gave you a formula before for one unstable eigenvalue, and if you stare at it, you can convince yourself it's equivalent to a simple projection, and this interpretation actually holds even for multiple unstable eigenvalues. So essentially what gradient descent does implicitly is it takes the negative gradient, which will point it outside of the stable region, projects it back onto the tangent space of the stable region, and then just takes a step in that direction. And this interpretation is really nice, because you can start to actually ask and answer many questions about gradient descent that you couldn't before. So for example, we had these loss curves that seem to go down in the long term, but gradient descent was doing so non-monotonically. So what's going on? This gives you a very simple answer. This object here, the central flow, has a monotonically decreasing loss. This is a very short calculation. It's just the fact that a projection is going to be correlated with the original vector. So if you take the inner product of this projection with the gradient, then you'll just get a negative number. So the central flow has a monotonically decreasing loss, but then you add to it these oscillations. And the oscillations can fluctuate and cause the loss to be non-monotonic. But this is the real notion of progress for gradient descent. So I actually just want to show a simple animation for how it does, what the actual stabilization process looks like for multiple unstable eigenvalues. So for one, it was this picture where you kind of enter this red region and you catapult it out. But for multiple unstable eigenvalues, the picture is really funny. And it's partially I just wanted to show this because the picture is pretty, but partially because it actually just underscores why theory is hard. So what I'm plotting here is the red are the eigenvalues of the Hessian, which I'm writing as an ellipse. I'm just going to plot two eigenvalues. And this dashed line is the stability threshold. So whenever the ellipse leaves this circle, then it means we're unstable in that direction. And with this arrow, the black arrow, I'm plotting the direction in which gradient descent is actually oscillating at a point in time. And you can see it's like some very complicated dynamics. It turns out these dynamics are formally chaotic. And it's essentially just playing whack-a-mole. So what it's doing is every time an eigenvalue leaves this region, the direction in which you oscillate rotates to match that region, and you force that eigenvalue down at the risk of allowing the other eigenvalue to exceed 2 over eta. Then you're like, oh no, the other eigenvalue has exceeded 2 over eta. So you go back into the other direction and try and track that one too. So somehow in oscillating in one direction, you're trying to automatically bring all of these eigenvalues down. And so you get this very complicated dynamical system. So I claimed that this isn't just pretty theory, but the goal is to actually get something that empirically makes sense. And this is especially important because we're not doing any rigorous math. So if we don't have good empirics, then the theory is worthless. So I want to show some empirics here. So this is a standard gradient descent trajectory. So this is again a vision transformer on CPAR 10. And you can see that the loss goes down non-monotonically, and you get these oscillations in the top eigenvalue of the hash. So if we smooth this trajectory, this is just what happens if you literally apply like a Gaussian smoothing to this loss function, to this loss curve. And I'm also going to plot the central flow on top, and you get an incredibly good match. And so we're able to predict essentially the entire optimization trajectory of gradient descent using the central flow. And in contrast, gradient flow is a terrible approximation. So here, this is gradient flow not obeying the sharpness constraint and just veering off to infinity. And we can see it's actually a really bad model of gradient descent.
How hard is it in these situations to solve this complementarity problem?
The complementarity problem is always a low-dimensional complementarity problem, so it's very easy.
Okay.
The dimension of the complementarity problem is just the number of eigenvalues that are currently unstable. So here it's just a two-dimensional complementarity problem, not so bad. And in general, it'll go up to 10, 20, but it'll never be super high dimension.
But do you have a theory for how the eigenvalues under even gradient flow in this model would have, like, how do you know how the case eigenvalue?
We're simulating this explicitly on the Bishop transformer. So we're
But
simulating.
you're measuring like
Yeah, we're measuring it. So we're measuring it in the same sense as like you compute gradient flow. Like when you say you run gradient flow, it's not that you have some closed form, it's that you just simulate this doing some like Euler discretization. And we're doing the same thing for the central flow. So at every step, we compute how many eigenvalues we expect to be at edge stability. We project the system down into these directions. We solve the complementarity problem, compute dw dt, and take a step. And that's how we're getting these predictions for the central.
Just to compare with the original gradient flow. So the original gradient flow, you would have said the top eigenvalues get driven to, the minimum very quickly, and then, less.
Yeah, like here the eigenvalues are just going to.
And that's still happening here, just they have this secondary effect of constraining into this.
Yeah.
Allowed stable region.
Yes.
Okay.
So you should really think of gradient descent as gradient flow constrained to the stable set.
Yeah.
But like I think
To get this central flow curve, at every point I need to solve a few top eigenvalues of Hesse.
correct.
Then if I have a very large model, why don't I run the arbitrary gradient descent and do Gaussian averaging and get the same curve?
Of course. I mean the central flow is not an algorithm you should run. It's a theoretical tool. So the goal is like it's at least easier to do math with the central flow because it's a continuous time process.
Yes.
But you should never run it in practice. It is going to be at least 1,000 times slower than just running gradient descent.
But what insight can we get in addition to the series? Very nice. What insight can we get?
So
yeah,
I
can get the curve match, but then the curve matching I can just do quick Gaussian smoothing of the empirical
yes.
gradient descent.
Yeah, but then you can start to actually get things like convergence rates. You can actually start to get things in terms of even just like why does the loss go down is a non-trivial question for gradient descent. Like the fact that the loss doesn't decrease monotonically for gradient descent, but does over long periods of time is not something you can understand without some sort of tool like this. But in general, I agree that this is not going to directly give you a better optimizer. Like this is not intended to give you a better optimizer directly. But the goal is at least to describe what's actually happening when you use gradient descent. And this is more just a proof of concept to show that we got the answer right. I think the most important plot here actually is not the loss, but this distance plot. So here we're actually showing the distance in weight space between gradient descent and the central flow over time. And in blue, I'm measuring the distance between consecutive iterates of gradient descent, so Wt plus 1 minus Wt. And in black, it's the distance between gradient descent and the central flow. And you can see that gradient descent is much closer to the central flow than successive iterates are to each other, meaning that we've really got the answer right. On the other hand, gradient flow like shooting. So it's at least showing that like this differential equation is correct, but it doesn't have any practical applications. More interesting theory actually pops up for Adam, and I hope to get to that ahead of time. So the other claim that I want to make is like gradient descent is itself should be treated almost philosophically as a perturbation, a noisy perturbation of the central flow. And to make this point, I'm going to show two network outputs. So these are the logits of the network, probabilities it's assigning to different classes over time. And you get a plot that looks like this. So gradient descent is oscillating like crazy in a really strange pattern, while the central flow evolves smoothly and it predicts the time average as it should. But you start to get really weird things. So for example, look at this bottom plot. This bottom plot will be telling you that if you run gradient descent and you ask it like, is this a cat or is this a dog? If you check it on an even iterate, it'll say dog, and on an odd iterate, it'll say cat, which just seems like a really bad idea. And not only that, but it's going to be fairly confident in its predictions, right? Like the logits go up to like 0.3. So it's going to confidently tell you it's a dog, and at the next step, it's going to confidently tell you it's a cat. And it really thinks neither. It's actually very incompetent about its prediction. And so if you just look at the raw gradient descent iterates, you can easily get. And the last thing is like, I've been using a vision transformer as like a running example, but everything holds for pretty much any architecture you can imagine. Yeah.
Are you doing all these literally with the gradient, or is it a batch?
These are all full batch gradients.
I've got a full batch. I mean, if you did some realistic batching, how would the noise compare to the effects we're talking about?
Yeah, so this is something I'm currently working on. It gets very complicated. You enter multiple regimes. There's some intermediate regimes in which you get some sort of instability, but not exactly matching this. If the batch size is large enough, it will exactly match this. Yeah, work in progress, but currently we don't know.
Yeah, is it actually well understood what kind of implicit constraint SGD imposes on
No.
the head? Oh, like the
Maybe in 6 months.
Okay.
No. Any other questions? Oh. So, yeah, now I want to talk about Atom because I think this is where the math gets a lot more exciting. So, for gradient descent, not everything that I just talked about, but at least some of it was actually a previous paper of mine where we did actually manage to analyze these dynamics rigorously. Like we wrote down the chaotic system, we analyzed it, we tried to show some self-averaging. It was an absolute disaster. The theory is not that strong, which is why we kind of gave up on doing things rigorously. But I think more importantly is once we gave up on trying to do things rigorously, we were able to easily, with like 2 extra lines of work, extend it to more complicated optimizers like Atom, which would be completely hopeless to analyze from scratch. And so I wanted to show what the conclusions are for Atom. So here I'm doing the RMS prop, which is a simplification of Atom without the momentum. So you still do the adaptive learning rates, which go in the denominator, but I'm not doing the momentum numerator. So the way Atom works is you take the element-wise squared gradients and you maintain an exponential moving average of them. That's going to be my nu. And then I'm going to use these to determine effective step sizes per coordinate for gradient descent. So despite Atom's success, it remains completely unclear, at least to me, why this is a good idea. This looks really weird to me. It also doesn't obey most ideas in classical optimization theory. And so it really seems like a strange algorithm. So the other observation is you can write this as preconditioned gradient descent. So if you define this preconditioner to be the diagonal matrix of eta over root nu, then RMS prop is just gradient descent with this evolving preconditioner T. So I can just rewrite this update in this more compact. And for preconditioned gradient descent, we understand what stability looks like, at least for quadratics, which is how we're going to define edge stability for adaptive optimizers. So local stability, if you just did gradient descent on a quadratic, is going to be given by the eigenvalues of this effective Hessian, where you precondition the Hessian by this preconditioner. This is not a symmetric matrix, but you can symmetrize it and show that all of its eigenvalues are real. So this equation makes sense. And just as for gradient descent, edge stability just implies that this value will grow, like this lambda max will grow until it reaches 2, and then it will stay at 2 for the rest of training. And that's exactly what happens. So I want to show how you derive the RMS prop central flow. And I'm just going to kind of skip to the answer, but I want to give some intuition for what changes compared to gradient descent. So the first thing is that for gradient descent, we saw that when you oscillate, the gradient gets replaced with the average gradient. And this is still going to be true. So RMS prop is still going to oscillate, and these oscillations are going to add some extra term, some curvature penalty to this gradient here, when you try and convert this to a continuous time process. But the other thing that happens for RMS prop, which is new, is that as you begin to oscillate, the gradients kind of spike, right? Because if you're oscillating, then you're taking these really, really big steps. And so the gradient gets really big, which makes this nu also really big. And what that does is it decreases your step sizes, which will restabilize training. So now the oscillations have 2 ways of restabilizing training. Either they push you to a flatter region where the Hessian is smaller, or they push you to use smaller step sizes, which can also restabilize training. And the correct answer is going to be some balance between these 2 forces. So if you actually try and analyze this like directly, like you try and analyze this dynamical system, it's super complex. I can show plots for it if people are interested, but I think there's virtually no hope of getting any sort of nice conclusions for these actual dynamics. There's just too many moving parts. But this time averaging argument, where you just close your eyes, pretend it oscillates with some covariance, and then just compute what this covariance would have to be in terms of a fixed point equation, it's still really easy to carry out. So I'm not going to show the calculations here, but they're pretty much exactly the same as for gradient descent. I just want to jump to the answer. So this is what the answer looks like. So the answer is going to be something in the form dw dt is some preconditioner p that I'll describe in a second, times some average gradient, where the average gradient is going to be the original gradient plus some curvature penalty. And now I have to describe what p is. So if we ignore this curvature penalty, p is going to be a diagonal preconditioner. And this diagonal preconditioner is going to solve what to me was an absolutely crazy equation. It's going to solve max cut. This was not some relationship that I expected. I've never seen this mentioned in the literature. So this is the dual to the max cut SDP. you're looking for a diagonal preconditioner P with minimum trace, subject to some semi-definite constraint. So my claim is now really crazy. As you run Atom, at every step, implicitly what Atom does is it will solve this max cut SDP, compute this optimal P, and use that as its preconditioner. This is a really crazy claim. I will justify it empirically in the next slide, but this is what I claim the RMS prop central flow is. But it's not just this. It's not just preconditioned gradient flow. There is a curvature penalty as well. And, oh yeah, I should also mention this h less than or equal to 2p is a very natural constraint. It's equivalent to p inverse h less than or equal to 2, which is what I mentioned is the stability condition for RMS prop and for adaptive optimizers more generally. And now you have to kind of do some inverses in your head. If the learning rates are 1 over p, because you're doing a p inverse in the preconditioner. So minimizing the trace of the preconditioner is equivalent to maximizing the harmonic mean of the learning rates that you use. So you can rewrite RMS prop as at every point in training, compute the learning rates that are locally stable with maximal harmonic mean and use them to take a step in the gradient direction. I don't know how you could possibly have predicted this formula without something like the central process. But then there is this extra term, this curvature penalty. And this curvature penalty can be interpreted as I want to move in a direction W that will decrease this trace even further. It's the gradient of the trace, which tells you I want to move towards areas in the loss landscape where I can actually use larger learning rates with a larger harmonic mean. Equivalently, I want to move towards flatter regions of the loss landscape so I can take bigger steps. And now this kind of starts to give a hint towards the secret of Atom. So we call this general principle acceleration by regularization, and we demonstrate through a bunch of ablations that it's really key to why adaptive optimizers work. So there are two parts to Atom. The first is use the largest step sizes that you can. Largest meaning largest harmonic mean, but still, I find myself at a point in weight space, I'm going to compute the largest possible step sizes and use these step sizes to run gradient descent. But I'm also going to add this curvature penalty, which tells me to move towards regions of the lost landscape where you can actually take larger steps in the future. So what happens is that I regularize, which drives me towards flatter regions of the lost landscape. Once I'm there, I can use larger learning rates. I'm going to continue to regularize, continue to use larger learning rates. And empirically, you can actually show that these step sizes increase over time. And they increase over time because you're constantly driving yourself towards flatter regions of the lost landscape. And so this general principle of acceleration by regularization is really important for Atom. And the easiest way to test this is you can just delete this term from the central flow. If you just use the same learning rates, but you delete the curvature penalty that comes from oscillation, you'll get a really bad optimizer. So again, we trained this on a bunch of different architectures. So here we predict the loss, we predict the gradient norm, we predict how much you oscillate, pretty much everything. So empirically, it seems like this is a very good match for the dynamics of RMS prop. And as I promised, I claimed that the preconditioner solved max cut, which again is an incredibly strong claim. So we checked it. So what we're doing here is nu is the preconditioner. We plotted it over time. These are a bunch of different coordinates. So we just randomly sampled 10 coordinates of the preconditioner. And at every point in time, we're also solving the max cut SDP exactly. And you can see that they line up pretty much perfectly. So the effective learning rates used by Atom really are coming from max cut, which I find incredible. And yeah, this is true for many different architectures. So just to wrap up, the way we propose to study optimization is by deriving central flows, which are intended to model the time average trajectory of oscillatory optimizers as a way to address the fact that it's really hard to analyze oscillations. And then after we do this, albeit heuristically, we actually verify this by computing them on real neural networks and real data sets and show that for a very long period of time, for the entire training trajectory, we're able to predict the optimization curves. And finally, by interpreting these flows, we can actually read off some of the optimizer's behavior that was not at all obvious from the raw formula. So I think the easiest example for this is just this connection with max cut for Atom. So more like generally, I think there's some weird takeaways that took me a while to internalize. So all of these answers, all of these central flows, somehow are higher order optimizers. So for gradient descent, I'm claiming that gradient descent is implicitly implementing a curvature constraint. But implementing the curvature constraint actually requires you to compute third order derivatives of a loss. So it's not even a second order optimizer, it's a third order optimizer, but you're only giving it access to gradients. This is already pretty incredible. And the idea is that by using differences in gradients nearby, you're able to approximate Hessians or higher order terms in the loss. And the second is this general principle of acceleration by regularization that I personally think is severely underexplored in deep learning. It's somehow switching the causal structure of the way people think about optimization. You shouldn't think of it in terms of how do I adapt to the loss landscape? How do I improve the condition number of the loss landscape? You can start asking questions like, how can I force my optimizer to put me in regions of the loss landscape that are easier to optimize? And this flipping of the causal structure of optimization, I think, is really important. And we just don't yet understand how to do this properly. But Adam is a good prototype for how to do it. And finally, just this clickbait that RMS prop implicitly solves max cut the determinants diagonal recognition. I also have some interesting ideas for future work. So the first is just rigor. As I mentioned, the whole derivation here is super sketchy. So under what assumptions can you actually make any of this rigorous? I have some thoughts on this, but I probably don't have time to go into it. And just more generally, what do reasonable assumptions for deep learning look like? I can't assume that my loss function is going to be smooth. I can't assume higher order smoothness. So it starts to be really unclear what I am allowed to assume on it. But if I can't assume anything, then I can't do anything. So what does a reasonable assumption even look like? For noise, can similar arguments be used to derive a central flow for SGD? And more philosophically, does a central flow for SGD even exist? So what does this mean? SGD is a random process. And so what it would mean for a central flow for SGD to exist is that if I run SGD with multiple random seeds, these trajectories in weight space won't deviate too much. That way you could hope that taking the average of all these random seeds would actually give you some reasonable trajectory. And the answer to this is like sometimes yes, sometimes no. And finally, in terms of applications, none of this theory is intended to actually be directly prescriptive. This is purely a predictive theory for now. But can it actually be used to select the type of parameters? And can it be used to design new optimizers? And I'm actually especially excited about this direction here, because I think one of the challenges in replacing Adam is that if we don't understand how Adam works or why anything that it does is a good idea, you have no hope of designing an optimizer from first principles that will outcompete it. And so at least by shedding light on some of the ideas that make Adam work, I'm hoping that it'll inspire some optimizers that make these implicit ideas fully explicit. So that's it for my talk. Thank you for listening, and I'm happy to take any questions.
It was a really nice talk. What happens with momentum?
Excellent question. So I actually do have, the answer is the chaos gets even more chaotic and I don't know how to handle it. So,
but we like momentum a lot.
We do, which is a problem. So like, let me show you what goes wrong. I actually have an animation here that is fun. So what I'm plotting here is I'm running gradient descent. I'm running Adam on a one-dimensional quadratic. So literally my loss function here is just like x squared over 2. The simplest possible function. It's in one dimension. Adam has 3 variables. A state variable x, a momentum parameter m, and a preconditioner nu. So I'm going to run Adam for a very long time. And for this setting of hyperparameters, this is the limit cycle that it converges to. I have absolutely no idea how to describe its limit cycle. More importantly, I don't know how to compute its covariance. For the central flow, the most important thing is, given some sort of chaotic process, can I predict in advance what the covariance has to be? Can I compute some fixed point equation it has to satisfy? These equations don't close for Adam. And because they don't close, I don't know how to compute anything about this process. And so I can't get a central flow. And you can have a lot of fun like messing around with the beta 1 and beta 2 parameters. And you can get some really crazy limit cycles or curves for what Adam can do. And for none of these hyperparameters do I understand. So the green region is simple. The green region is this region in which the momentum is small enough that things are fine and it doesn't hurt you. Here it degenerates to a period 2 fixed point. This I understand. This is the same as for RMS prompt that I already described. Here we have a central flow and it works. But for the region that people actually care about in practice, I have no idea what these curves are.
Aren't defaults like 0.9 or something? So
0.9, 0.95, yeah. So somewhere here. I don't know. Yeah, looks like something like this. So my question is like, in terms of beta 1, beta 2, compute the like moments, even just the variance of this process. I have no idea how to do it. So anyways, this is why I don't know how to solve it.
Do you have a sense in these problems of like, as a function of training time, how many of these eigenvectors are like saturating the stability bound?
I think the answer is like for reasonable problems, all of them will as fast as possible, but all of them meaning all outlier eigenvalues will saturate the stability bound. The number of outlier eigenvalues tends to be the number of classes of the problem. So on CFAR 10, you'll have 10 outlier eigenvalues, CFAR 100 outlier eigenvalues, and they all seem to saturate pretty early. Yeah. Any other questions?
Do you have any, so you said that empirically, you're partly explaining why gradient descent might generalize better. These models that generalize better than gradient flow. And now you told us, well, one difference is that according to the central flow, it stays within the stable region. Now, is that somehow connected to generalization?
Yes, but in ways that no one understands. So this actually goes back to, there are all of these empirical results that neural networks trained by SGD with small batch sizes and large learning rates generalize better. And somehow heuristically, the theory that's been thrown around is like SGD converges to flatter minimizers. That part is actually rigorous. But then like flatter minimizers generalize better. And this explains the improved performance. The second part of the conjecture makes absolutely, like, it's not a rigorous statement. It cannot be easily made a rigorous statement as far as I'm aware.
It makes some sense. It's just not
And it also doesn't hold up. It's not really, you shouldn't take it seriously.
It doesn't hold for all models, yeah. Like, I think this was like some overfitting potentially to like specific, like theorists love to work on like ResNets and CFAR10 or CFAR100. This is like the theorist test bed. And I think that for these models, the correlation is very strong between curvature and generalization. There are some more recent reports that like for transformers, this connection may be weaker. And in general, this story feels very fuzzy to me. So it is true empirically that on many settings, especially computer vision settings, lower curvature implies better generalization for reasons that I and no one else understands.
Or even like simple Bayesian arguments.
I don't really know about the Bayesian arguments, because the Bayesian arguments are somehow saying that like the good minimizers will take up like more, there's something about like mass and weight space, but really this is saying that like if I sample from this distribution, then I will generalize. But like you're running an actual algorithm that's not sampling. Like in this case, it's a flow. And so
I didn't say it was a proof.
no, yeah, it's like it doesn't feel crazy, but I just don't know how to like make it mathematical. And so in general, I'm very scared about these statements about generalization. I just don't understand.
But claiming that cutting off or pushing down the top eigenvalue would seem even farther, even less well understood. Why that should help generalization.
I think it's not clear what measure of flatness is the correct one for generalization. Like you can argue trace in some other metric. You can argue largest eigenvalue.
Just I say it's really dominated by the large eigenvalues.
Yeah. I don't know.
So I found the oscillations of the predictions, like the output logits, kind of disturbing for the reasons you mentioned. Like, you stop at this time step or the next time step, you're getting completely different predictions. Is there something you can do algorithmically to like smooth out
weight averaging?
Or even weight decay where you're kind of like averaging. It won't do it. So you have to literally average the.
I think there's no excuse for not averaging weights in weight space, like stochastic weight averaging, in any situation for neural network training. You can also decay learning rates if you want, but I think like it's super cheap, does not require much memory. I just like don't see why you would not always decay, or why you would not always compute exponential moving averages of your actual weights before computing any sort of downstream metric. I mean, like consistently, like the loss will be significantly lower, test accuracy will be significantly higher. Like, yeah, I think you're just throwing away training time and information if you're not averaging your weights. In this case, you need to average your weights over a period of 2. Not so bad.
I wanted to ask about SGD. Your analysis reminds me of like some parallel analysis of the SGD, which I'm sure about. So around the zero loss manifold. So here, the difference here is that you actually have a surface that separates the stable versus unstable. You show that you essentially move on that surface, but with these fluctuation deviation. So over there, that manifold is essentially zero loss, and then SGD causes you to fluctuate around that. That essentially triggers a third order effect flow on that. And then you can show that you can move toward flatter areas.
Yes.
So how difficult is that to bring to incorporate SGD in your current time? Do you think these two are very, just on the surface they seem similar, but maybe they're actually two different things?
So they're very similar, and in fact, that line of work is exactly what inspired us to look at cubic Taylor expansions of edge stability. There are a lot of differences though. So I would say one thing is these theories that you're describing really only hold at the end of training and for like really infinitesimal learning rates. So I actually tried to test these empirically at some point and see how far you work from these limiting flows. At any reasonable learning rate, you're never close. But if you set your learning rate to like 1e minus 10, you'll see it. So like it is possible to simulate it, but it's very difficult. And I suspect that there should be something that holds early learning rate. Like my goal would be some version of the exact same theory, but instead of restricting to the zero loss manifold, just like holding throughout training. The issue is that there are some other effects that show up here. So in these papers that you mentioned, the limit gets set so small that stability issues are never relevant. But I think it's not, like, I think in the practical regime for SGD, stability issues are relevant. And in general, I think it's not surprising that you see stability issues because practitioners are greedy. You're going to take your learning rate and try to double it. And if you can double it, you will. And if that works, you'll try to double it again and again and again. And the only way for this process to stop is for you to hit a point where if you doubled it again, it would blow up. And if we want to understand optimization in deep learning, that's the regime we want to understand. And so I think you do have to grapple with stability issues for SGD, which I think are just not that well understood. Any other questions? Great, thank you.